Welcome to part 7 in support of our video series on hypothesis testing. In this video, we will discuss use of the z-distribution for performing inference on the difference in two population proportions. I'm Renee Clark from the Swanson School of Engineering at the University of Pittsburgh. So, when might you need or want to perform inference for the difference in two proportions from independent populations? Okay, so for example, you might need to explore sedans versus full-size trucks in terms of each of their reliabilities. Okay, let's say that P1 is the proportion of all sedans that break down on the road before accruing, say, 50,000 miles. P2 would be the proportion of all full-size trucks that break down on the road before accruing 50,000 miles. You could use inference on the difference in two proportions to determine whether these population proportions differ. Okay, I'm going to jog your memory a little bit. As you'll recall, this is how we calculated the confidence interval for P1 minus P2, okay, or the population proportions from two independent populations, okay. So we used the difference in the p hats as the point estimate. We used the z-distribution, or the normal approximation to the binomial. And under the radical, we used the individual P1 and P2 hats as such. Okay. Now, our typical null hypothesis when we're performing inference with two population proportions is that P1 equal P2, okay? And of course, another way to write that is that P1 minus P2 is 0. So in other words, there is no hypothesized difference in the two population proportions. Okay, so two things. I'm going to call your attention first to the z random variable, or the z test statistic, that we're going to use for inference on two proportions. Okay, now notice its similarity to the confidence interval, and that's why I first showed you the confidence interval. Okay, so as our point estimate here, again, you'll see the difference in the two p hats. Okay, now because we are hypothesizing no difference in the two population proportions, in order to do a proof by contradiction, that hypothesized difference gets inserted into the test statistic, and of course that term vanishes to 0. Okay, now under the radical in the denominator, you'll notice that it has a similar look to what's under the radical for the confidence interval. Okay, has quite a similar look. But what you'll notice in the denominator here is that we have a new quantity simply called p hat. P hat times 1 minus p hat, and then times 1 over n1 plus 1 over n2. Okay, so let's discuss where this p hat comes from. Okay, it goes back to, again, where we are hypothesizing no difference in the two proportions from the two independent populations. If we're hypothesizing no difference, then P1 equal P2, and we can simply replace that by one variable called P. Okay, so in order to estimate this 1P, which we will call P hat, what we can simply do is we can pool pool, you've seen that term before with sample variances, we're going to pool the information from the two samples out of the populations. In the numerator, we are going to pool the counts or the number of successes, okay? These two are, of course, binomial random variables, right? Y1 is number of successes from the in the first sample. Y2, number of successes in the second sample. These are binomial random variables. And then in denominator, we're simply going to pool or bring together the number of trials in each case. Okay? But again, because we're hypothesizing that those proportions are equal, it makes sense to pool them in order to get one estimate p hat, just like we did when we were assuming or had reason to believe that our population variances were equal. Remember, we used the pooled estimate of the sample variance. Same thing here, okay? So then in the denominator, that's what appears here in the denominator of the test statistic is p hat, that's your pooled estimate, p hat times 1 minus p hat times 1 over n1 plus 1 over n2, square root thereof, and that's what's in the denominator for the z random variable. Okay, now in order to use the z distribution to do the inference, we have to meet the following two key assumptions, which should look familiar to you. We say p hat times n1 plus n2 must be greater than or equal to 5. And again, this is the pooled estimate that we just discussed, right? Equal to y1 plus y2 over n1 plus n2. And remember, p1 hat was y1 over n1, p2 hat y2 over n2. Okay? And then that's assumption 1. Assumption 2, which should also look familiar to you, is that 1 minus p hat times n1 plus n2 must be greater than or equal to 5. Very similar in flavor to which you've seen before when working with proportions. Okay, and finally, let's talk about the relationship of this to the confidence interval. Okay, again, our typical null hypothesis is that P1 equal P2. And another way to write that is P1 minus P2 is 0. So in other words, no difference in those two proportions. Okay, so let's say I calculate the following confidence interval representing the difference in two population proportions. So negative 0.6 to 0.2. Okay, so in this particular confidence interval, starred in blue here, 0 is contained in that interval, right? So 0 is plausible for P1 minus P2. So we certainly would not reject that. We would not reject 0 as a plausible value for P1 minus P2. Okay, so we would, in this case, fail to reject the null hypothesis. Okay, however, let's say that this was the confidence interval that was calculated for the difference in the proportions, 0.3 to 0.4. Okay, so in that case, for the confidence interval in red, 0 is not contained in that interval, right? It falls below 0.3. Okay, so in this case, 0 is not plausible for the difference in the two proportions. Okay, so in this case, we would reject 0 as plausible for P1 minus P2. So we would end up rejecting the null hypothesis in this case. We wish to thank the National Science Foundation under Grant 233-5802 for supporting our work. Thank you for watching.